out a new topic. Okay. It's using an op-amp with just one DC source. Okay. As you see in the figure on the screen. Okay. Now, when we use, we have a positive supply and a negative supply most of the time. But to create positive and negative supplies causes problems, causes double the price on a power supply. So sometimes we operate op-amp with a single supply, single voltage supply. But when we do that, normally we'd have 0 volts, 0 volts on the output, but that's only what, VB over 2, where VB is what we used to call VCC. Right. So if VB divided by 2 is on this output, it's also on this input, because no DC current flows, and the voltage that's here is also the voltage that's there. Okay. So to make sure this voltage is VB over 2,
one question before you go on this a new topic or just a continuation from last class?
Young man, you came late.
Oh man, I only come 2 minutes late, man. Or 1 minute.
You are still late. I don't go back on material with latecomers.
Oh man, that's Dr. Cadre, man. Come on, man. That's only a minute, man.
It is 2 minutes, and you still wasting my time.
Come on, 5, 9, man.
This is in the textbook.
Hey, thanks.
So we have VB over 2. I don't understand why people think that you could be 2 minutes late. It's all right to be 2 minutes late. I mean, that boggles my mind. Anyway, so half the VCC is going to be at the output. So if half the VCC is also going to be here at this input, because there's no drop across this resistor. Okay, that means we're going to have to supply VCC over 2 to the non-inverting terminal, because the voltage of the non-inverting terminal has to be the same as what's at the inverting terminal. Okay. Now, if there's voltage, if there's DC voltage on the output, then we need this capacitor here. What is this capacitor called? From 235, what is this capacitor called? Wow. Y'all gonna graduate not knowing anything. It's called a coupling capacitor. A coupling capacitor. The same is true of the input coupling capacitor. The purpose of the capacitor is to pass AC. Pass the AC. The same is true of the input. CI, that's the input coupling capacitor. Now, what do you think? What do you think we need CI to do? What kind of reactance do you think we need CI to have?
I'd say for it to be high.
Why do you want to be high, Mr. Johnson?
Because if the capacitance high and the resistance probably low, and then
you see, wait. You see, you are changing what I asked. I asked, what do you want the reactance to be? Y'all don't listen carefully and you don't read carefully. And it shows that little assignment you just turned in. Okay. I didn't ask anybody in the magnitude plot, okay, to mark your frequency and dB. I asked nobody to do that. What I actually did was to mark the -3 dB point. The -3 dB point is what I asked for. You don't listen carefully and you don't read carefully. Let me go back to that statement I just made. What I asked for was this. If you did the Bode magnitude plot, okay, and you did it far enough away, you'd have found out that it drops to -3 dB. And I asked for this frequency here. That's the highest frequency I asked for. You could have gone over that, but you would have had to select that point. Let me know that is a -3 dB frequency. Only a few people did this. The rest of you gave me, let's say your frequency is 10 kilohertz. You selected this. And that's gonna be close to 0 dB. Okay. Well, that's fine, but I didn't ask for it. And some of you stop right here. Some of you stop right here. This is where you stop. Even though the question says your highest frequency is at the -3 dB point. It said that. You must learn to read properly. While I'm here, what strikes you strange about this? What's the theoretical? What's the theoretical dB? Well, that all pass filter, what was the theoretical dB?
Wasn't it 0? 0 dB?
0 dB for every frequency. That's what we had theoretically. But with a real world op amp, this is what we get. And that's all I was pointing out. So an op amp does not work ideally. What does this remind you of? What does this magnitude plot remind you of?
When we was doing the lag.
When you were doing what? Sorry?
The lag.
The what?
The lag. When we was the lag circuit.
Really? Tell me, how do you get that from this? What you just said to me, how do you get that from this graph? How do you know? Why would you say this looks like the lag circuit?
I was just assuming, because the lead and the lag, they differ, but they
only differ in phase. Am I plotting the phase diagram?
You're doing the magnitude.
So why would you think about the phase? Again, I
I mean, that
ask.
look like a low pass filter.
Exactly, Mr. Pintoid. Exactly. That's exactly what I want to point out to you. The all pass filter theoretically isn't a low pass filter. There's no low pass filter involved.
Oh, they got it right.
Yes.
I have a question, right? Like,
Let me finish my statement.
uh,
Okay. But a real world all pass filter behaves like a low pass filter, and this is the cutoff frequency right here. That's the cutoff frequency. So we can't use it as a all pass filter. We can only use it up until this right here, FC. Yes, Mr. Pinto, what's your question?
when with this filter, I noticed like when you run the when you give it a long time, like a wide frequency range, like if you go up to 1 meg or like 1 gig, the graph has changed. It don't look the same as the other ones we've been doing.
That's exactly right, because it is not the same as what we've been doing.
Now, it would have been okay to show that on the assignment, right? That part,
Yeah, but Miss Pinto, I look quickly at you didn't identify this point.
No, I didn't. I was just talking
okay.
about the
But
time.
what you did was fine, except that I asked for this point to be identified.
Right. Okay. I just wanted to make sure that the amount of time I run it for was acceptable or not. You see, if you wanted to see that or not.
Yes. As long as you ran it, you chose a bigger frequency range than I asked, and had you put in the frequency that I asked for, I would have given you full marks. But you didn't put in the frequency I asked for.
Right.
Okay. Any other questions about this while I think of it? Any other questions about the homework? Now, there's one person who sent me design that clearly did not work. The graph, he sent me correct phase graph, but the phase graph clearly showed that he didn't have 135 degrees at his frequency. And yet he just submitted it. I mean, that tells him his design doesn't work. And by the way, let me say this. There was a person who thought, I graded those who came in before 12 o'clock. Well, before about 11:45. I graded those. Some of y'all are thinking, I'm designing for frequency. One person actually gave me the percentage error in frequency. That's not what I asked for. I was designing for phase. You're designing for phase in this assignment. I give you the frequency. I ask you, at this frequency, I want a phase of 135 degrees. And you either have it or you don't have it. And if you have it, you better be within 5%. So this person was checking for frequency. Why? You should be checking for phase. So clearly that person didn't understand what he was doing. He didn't understand what his goal was. Folks, you must learn to read carefully. You must learn to listen carefully. Okay. Any other questions about that homework? About that test, I should say. And then somebody sent me a page that I have to rotate to read. That's a good way to get 0 for that page. You send me stuff that I can read properly, upright. First of all, I have no way of rotating that. Secondly, even if I did have a way of rotating that, I wouldn't. You send me stuff properly presented. And then another person thinks it's okay to write in pencil. Do not write in pencil. It doesn't take a good picture. All right. Let's get back to what I was asking. What I asked was this. These two capacitors, do you want high reactance or low reactance? Why do I hear silence? Folks, what's the purpose of this capacitor? I said it to you earlier. What's the purpose of this capacitor, these two capacitors?
You was breaking up when he was talking, but I think I heard you say that its purpose was to pass AC current.
And
I didn't hear the second part.
so we can't have a straight line there to pass AC current? A straight line wouldn't pass AC current? Why can't we just have a straight line there? Why do I need to put that capacitor in there? Let's go to the output then. Let's look at the output capacitor, the output coupling capacitor. Why couldn't I just put a straight line where the capacitor is? Let me try this again. If there's DC voltage now on this output lead. If we have two supplies, there is no DC voltage. There is DC voltage now on this output lead because we're only using one supply, and we got half of that supply on the output lead. What happens when I connect that directly to this output? That's RO. What happens? Nobody can tell me what happens? Wow. I can't believe nobody can tell me what happens.
If you put the you say put the DC source where RO it is?
No. I said I'm going to connect the output directly to the RO. That's what I said. What would happen? Folks, isn't it obvious what will happen? All right, let me ask a question more directly. What would be the DC voltage cross RO?
Wouldn't that be half of VB?
Exactly. It would be VB over 2. And if there's VB over 2 across RO, there'll be DC current through RO. And RO is our output. We may not want DC current through our output, our load. So how do we stop that from happening? How do we stop DC current from going through RO?
That's why you put the capacitor there.
That's why I put the capacitor there. Why? What happens for DC? Well, what happens to the capacitor for DC?
It filters it up.
That's too vague. What happens to the capacitor for DC?
It starts to charge.
And when it finishes charges, what happens?
It discharges.
Really? What makes it discharge? So when a capacitor charges, it then discharges automatically. Is that what you're saying, Mr. Johnson?
I believe when it's a dip,
When it's what?
when it's a dip, or if it loses,
When it's what?
when it has a drop in power, that's when it'll like discharge.
The capacitor is an open circuit for DC. How many times we said that in 235? The capacitor is an open circuit for DC. So as far as DC is concerned, that capacitor is not there. Nothing's there. It's an open circuit. So no current can flow from the output. No current can flow from the output of the op amp to RO. No DC current. However, for AC, how does the capacitor behave?
As a closed circuit, right?
As what?
As a closed circuit, closed switch, whatever. I think that's what it is.
Yes. But the capacitor will have some reactance. What do we want that reactance to be? High or low?
Don't you want it to be low in that case?
We want it to be low. We want it to be low as possible. We want the reactance of the capacitor to be low. Same is true for the input capacitor, except that there's an input source here. We have an input source here. And if this capacitor wasn't there, DC would flow this way to the source, maybe burning it up. We talk about all this, in 235. We talk about the purpose of coupling capacitors in 235. We want both of these capacitors to have low reactance. Low reactance, because we want them to look like a short circuit. We want them to look like they're not there for AC. It's just a wire as far as AC is concerned. Let me go over the page. Okay. I hope you all got a shot of this. As far as DC is concerned, that capacitor is not there. That capacitor is not there. So RO is not in the circuit. As far as DC is concerned. Of course, VI is not in the circuit because that's an AC source. How do I know that's an AC source? How do I know that's an AC source? All right. If that didn't say DC level, how would I know? How would I know that's a DC voltage?
Capital V.
Capital V and capital B. That's a terminology we use in most books. VI means AC or function of time. VI means VI of t. Okay. Capital V means DC. Capital V underline means phasor. There's a language to a book, and if you don't know that language, then you can't read the book. So the capacitor is not there, which means VI is not there, because I'm talking about DC equivalent, the DC equivalent. And of course, VL is not there because VL is DC is AC. So our DC equivalent then, DC equivalent is given by the top diagram. That's our DC equivalent. Notice RI is not even there. RI is not connected to anything from a DC point of view. Any questions about figure A? On the other hand, let's get the AC equivalent now. The AC equivalent. Ideally, CI is a short circuit for AC. CO is a short circuit for AC. The battery is a short circuit for AC. And so as far as AC is concerned, what do we have? This is what we have. An ordinary inverting amplifier with a compensation resistor of R over 2 and a load resistor of RO. Does this make sense, folks? Any questions about this? Okay. Let's go back here. We said we wanted the reactance of this to be low. What do we mean by low? What do we mean by low? Low compared to what? Low compared to what?
You asked for the reactance of the capacitance, right? Capacitor.
Yes, PI.
And you say it should be a low reactance, right?
Yes, but what do you mean by low? How low is low? Low is a relative term. Low relative to what? I mean, that's like saying something is small. Small compared to what? Folks, isn't it obvious? I don't know if you understand what we're trying to achieve here. We're trying to achieve this circuit here to look like this circuit here. Or this to be RC. As far as AC is concerned. This RF, this RI, okay, and here's RO. This is what we're trying to achieve. This is what we have. So this should be low relative to what? The reactance of this should be low relative to what?
Should it be low as Rn?
As low as? No, it should be a lot smaller than Rn because you want this entire combination to look just like Rn. You want that entire combination to look approximately like Rn. So what do you want from? Excuse me?
I say, okay, I get you.
So you want XCI to be what? A lot less than an Rn. And in engineering, what do we mean by a lot less than? We mean Ri divided by 10. That's the value we want XCI to be. Less than Ri divided by 10. So that when we add the reactance to the resistor, it is still approximately the resistor. So we've not modified the circuit very much. What about this output capacitor? What should that be low compared to what?
Compared to RO?
Compared to RO, yes. So XCO should be a lot less than RO. And XCO means less than equal to what? RO over 10. Any questions about that? So we mean then of what? 1 over 2 pi F CO is less than equal to R over 10. Okay, and let's take the equal sign. Okay. Well, okay. So what does that say about CO? 1 over 2 pi F CO. So RO 10 is less than equal to CO. Or another way of writing the same thing, CO is greater than or equal to 10 over 2 pi F RO. What F we're going to use? What F we're going to use? Okay. You understand that VI, the input voltage, the source, going to have many, many frequencies. Why? Because it's a signal. It may be a music signal. So it has many frequencies. Are we going to use the highest frequency or are we going to use the lowest frequency?
We use a high frequency.
Why? Is that the worst case scenario? No, it's not. We want to use the lowest frequency. We want to choose CO for the lowest frequency, because the lower the frequency, the higher the reactance. And we want the reactance to be below what? RO over 10. So CO is greater than or equal to what? 10 over 2 pi FL RO. I see. Okay. Similarly, CI is greater than or equal to what? 10 over 2 pi FL RI. All right. And what should R be? Let's go back to this diagram here. What should R be? You folks don't have the ability to take facts that you know and solve problems. And that's because you don't spend any time thinking about these things. What does R over 2 remind you of? What resistor does R over 2 remind you of?
Compensation resistor.
Compensation resistor. And what does the compensation resistor, what should its value be?
The parallel of RF and RI.
Well, there you go. So you have all the facts. Why are you not giving me an answer? So RC equals RI and parallel RF, but RC is R over 2. So R then must be what? 2 times RI and parallel RF. There's your answer right there. So now we have all we need to design an op-amp circuit that is one voltage, one battery source. And let's do an example. Okay, before was there a question? So this is the key. These are the key equations for inverting amplifier. Or inverting amp with 1 VCC, which we call VB in this problem. Okay. This is a key page that you need to understand. Now let's go to the non-inverting amp. Okay. Again, there's the non-inverting amp, but this time we need 3 capacitors. RI would have gone to ground, but it can't go to ground because there's DC voltage here now. We'd be shorting out that DC voltage. So we gotta block that DC voltage, but let the AC go to ground. Okay. We still gotta put half of VCC at the non-inverting terminal, so we still need this voltage divider. Okay. So we need this capacitor, which we call CI, in the inverting case, and there's our CO. Okay. So go ahead, please. Yeah, but you'll just look in the book and cheat. What would the DC look like? Okay, what's the AC look like? What's the AC equivalent look like? Okay. Why is this R over 2? Okay. Let's look at the original. Why is this capacitor CR over 2? As far as AC is concerned.
Because the VB would not be in the circuit anymore. And then towards the same value.
What would happen to it? What would happen to VB?
It'll like be shorted out the whole circuit.
It'll be shorted out. VB be shorted out. Therefore, R would be in parallel with R.
They're the same value.
They're the same value. Therefore, the equivalent be R over 2. And this capacitor be shorted. This capacitor be shorted. And this capacitor be shorted. So this would be the AC equivalent. And what's the gain of figure 533? By the way, the caption here is an error. This is non-inverting. Not inverting. It's non-inverting. What's the gain of figure 533? What's the gain? What's the voltage gain?
And the gain is RF over RI plus 1.
Plus 1.
Yes. In other words, it hasn't changed. Okay. So I can't tell. I think they call this CI now. This CI has to be small compared to what? The reactance of this CI is small compared to what?
The value of this, the input resistor.
This RI. Okay. This C out has to be small compared to what? RO. This C, the reactance of this C has to be small compared to what?
Are those both resistors?
Connected how?
Parallel.
In parallel, yes. Because this is the AC equivalent down here. This capacitor that's here sees R over 2. Okay, so it has to be small. The reactance has to be small compared to R over 2. Okay. Let's do an example now. An AC coupled inverting amplifier circuit is to be designed for application in which a single 24-volt power supply. The negative terminal ground would be the negative terminal would be grounded. Okay. The desired magnitude of the gain is 15, but the gain is really negative 15. The magnitude of the gain is 15, but the gain is really negative 15 because it's an inverting amplifier. To minimize loading on the source, the input impedance must be at least 10 kilo ohms. Okay. The output will be coupled to the circuit having resistive input impedance of 2.5 kilo ohms. That's telling us what the load is. That's RO, 2.5 kilo ohms. The reactances of all capacitors are required to be no greater than 1/10 the values of the corresponding series resistances is what? At 50 hertz. So the lowest frequency we want to amplify with this amplifier is 50 hertz. Specify components for the design. Okay. Well, I already gave you this. Okay. I already gave you this equation. Okay. And that comes out to be what? 3.183 microfarads. So it has to be greater than that. So we use a 3.3 microfarad capacitor, which is commercial value. Okay. And then CO is given by the bottom equation. Okay. So the capacitor has to be greater than 12.7 microfarad. So we use a 15 microfarad capacitor. Okay. And then RI is 10 kilo ohms. Oh, by the way, I think I gave you a wrong equation. I gave you a wrong equation. I gave you this equation. This equation is wrong. And I'll tell you why in a second. Okay, let's finish this off though. We got the two capacitors. We got the load that was specified. Okay. And RF is 150. So R over 2 equals RF. Now, why aren't they in parallel? I go back to the circuit. There is no RI as far as DC is concerned. The compensation resistor depends upon the DC conditions. But RI is not in the circuit. So R over 2, that's the compensation resistor, that should just be equal to RF. Because there is no RI. Okay. So I hope you understand the clarification. So RC equals R over 2, and that's just RF. So R equals 2RF. And to finish off the design, we make RF 150. We divide by 10 to get a gain of 15. Okay. And R is 2RF, so R be 300 kiloohms. Any questions about that? Okay. All right. I think that's all I want to do for today. I will send you an assignment on this weekend. Any questions before I say goodbye?
I have a question.
Yes, go ahead.
You mentioned your office hours a few weeks back. When it comes to the office hours, for example, let's just say doing an assignment and I have a question. Could I meet talks about that assignment? Not to get answers, but
no. You could email me. You could email me if you don't understand the question. But I'm not going to help you with the assignment. This ain't kindergarten. The assignment is for you to do. Now, if somebody is having a PSpice problem, I know that some PSpice problems are tricky. And
Yes,
I'll look at
PSpice be giving us a hard time sometimes.
But if that's because of your lack of ignorance, I won't help you. But if that's because PSpice is acting strangely, like this happened with Miss Butap, this assignment, PSpice didn't want the comma in 3,300 picofarad or whatever it was, nanofarad, whatever it was. I found out that you have to take out the comma and just write 3,300 picofarad. Now that's something strange. That's something that I didn't even know. After all these years of doing PSpice, I did not know PSpice had that problem. It took me a while when Miss Beauchamp sent me his design, and his design was right. I could tell that his design was right, but PSpice has given him wrong answers. And has given him wrong answers because of this strange property that PSpice has. Something like that I'll help you with. But if it's an ordinary connection of your circuit, I ain't going to help you with that. Okay? Because that's nothing out of the ordinary. That's something that I expect you to be able to do by now. Okay. But if you have a question about the question, not how to answer the question, about what the question is asking, I will entertain your question. But if it's clear to me that you're not even trying to understand the question, I will send to you. I'll tell you, read the question carefully. There is no problem with the question. Now, I admit to you that I'm human, so once in a while I send out a question that is incomplete, but not often. So when somebody's having a problem with a question, I'm willing to listen to what question they have about the question. And then I convince myself there's nothing wrong with the question. The problem is you. You're not reading the question carefully. You're supposed to read the question carefully. Okay. So I will not help you with your assignment at any time, my office or at any time. Anything else? By the way, any of you other profs do that?
Oh, you sound like you want to snitch, man.
What I'm thinking is, you all expect me to do that, but none of the other profs do that. I don't know any prof who does that. I'm going to give you an assignment, and then I'm going to tell you how to do that assignment. I'm giving you the test to test whether or not you understood what I said.
When you say the assignment be due? Oh, no, man.
Excuse me? Say again?
I was asking would the time frame be the same as last time, but due on Friday?
Say again?
Now I'm asking for what the time frame of the homework you're about to send, or will it be the same time frame as last week, or?
You mean when am I going to grade it?
No, when it's due, like, will it be due next week Friday?
Oh, I don't know. I haven't decided yet. I haven't written the assignment yet.
All right.
Does that matter?
Yeah, I gotta set myself up mentally for that.
Oh, Lord. Folks, this is all in a textbook. Some of y'all don't even have a textbook. A student who doesn't have the textbook is like a carpenter who shows up on the job without a hammer. Any other questions? All right. Have a good weekend. I'll send out an assignment later on. I don't know about today, but this weekend sometime.
That's it.
All right, Mr. Cartwright, take your time.
You too.